organic pigments that we suggested were produced through dissipative structuring using ultraviolet light in the UVC range on Earth's surface could also, of course, be formed in space, because in space there are starlight, and there are regions in which there are gas and dust containing these elements of life, which are hydrogen, oxygen, carbon, and nitrogen, basically. So we could imagine that these pigments, organic pigments, could be formed also in interstellar space, and of course on other planets of other stars, or even on other planets of our own star. So first, 99% of the organic material on Earth are made of these elements: hydrogen, oxygen, carbon, and nitrogen. And these are the first, third, fourth, and fifth most important or most abundant elements in the universe. So the first is hydrogen, of course, and the second is helium. But helium has a closed shell structure, so it doesn't like to form bonds with other elements. So that's a good reason for helium not being in the list of elements which are used in life. But there's also another reason, not only that reason that they're the most abundant, but also because hydrogen has 4 possible bonding structures. So there are 4 possible electrons which can form covalent bonds with other atoms. And that allows for a very complex 3-dimensional molecular structures. So the picture we see here on the left is called the Orion Nebula. And this is a very active star-forming region. So a lot of these stars are new stars which are formed in this region. Now, it may seem a little bit strange, but to form stars, you cannot do that just through gravitational collapse of neutral hydrogen or hydrogen with helium, which are the 2 elements which were suggested to have formed after the Big Bang. And the reason is that hydrogen has a proton and an electron. So it looks like a neutral particle, but if you get close enough, then because there's only 1 electron, it doesn't really shield the positive charge of the nucleus. And so you have like a negative and a positive charge. And if you put 2 neutral hydrogens together, there's an electrical repulsion between them. So even though you have the force of gravity, the 2 neutral hydrogens will very rarely stick together. So to form the seed for a star, we in fact need light. And this, as I will show later in the talk, is the UVC light. So without UVC light, or UV light, not necessarily UVC, but in the UVC ranges where most of the structuring is occurring, without this UV light, no stars would form. There wouldn't be gravitational collapse. And therefore no life, because we know that it's within the stars that these heavier elements, like oxygen and carbon and nitrogen, are formed through nuclear reactions occurring within the star itself. And then these elements are expulsed into the interstellar environment, usually through a supernova explosion or by shedding. As for example, we know the sun is emitting particles, and most of the particles are hydrogen, helium, but there are also some heavy particles which come off the sun, emitted to the sun. So these heavy particles can escape and go into the interstellar environment. And if the conditions are right, they could form molecules in that environment. Now, the idea of having molecules in interstellar space at first sounded impossible and rather ridiculous, because it was known that the temperatures of interstellar space are around, depending on how much material is in the environment, but around 4 degrees Kelvin, just over absolute zero. And it was also known that the densities of the material, even in very dense gas and dust clouds, is too small to have many interactions or collisions between the atoms. So it was thought that it would be rather impossible for molecules to form in space. But then it was realized that with UV light, ultraviolet light, one could form these molecules, and I'll get into that in more detail. And so, while this is data compiled in 2006, it is the organic molecules which up until that time had been found in space. And there were about 100 at that time, but now the number is about 400, greater than 400. And they detect these molecules through their infrared emissions, because they get excited by photons, for example, or could also be through collision, but basically by absorbing photons. And then they de-excite through emission in the infrared. So they have infrared emission bands, and they can detect them, and it's usually easier to detect infrared emission than visible emission, because infrared light, as you know, is not blocked much by, it's not absorbed that much by gas and dust. So they have found these different organic molecules, and now they have gone up to larger sizes. Here the table stops at size 9 atoms. It becomes more difficult when you get to much larger molecules, because there are many more vibrational modes. You know, there are 3n minus A's, where n is the number of atoms, vibrational modes. So you can imagine for a large molecule, you have so many modes that they just become smeared out, and it becomes very difficult to distinguish what is vibrating. So this is just showing that there are now more than about 400 organic molecules found in interstellar space. So we in this class have described these organic pigments as dissipative structures. That is, for example, starting with hydrogen cyanide in water and ultraviolet light, we can form the basis. And from the basis, we can form DNA, and then all of the other fundamental molecules of life, and up to the biosphere, the ecosystem. And we suggested that they form that way because they have this property of dissipation. And that is essentially what nature is doing, it's dissipating. That is the second, based on the second law of nature, that the entropy increases. Or if you like to say it in other words, that the energy of a certain object or photon or particle becomes ever more distributed over more degrees of freedom. So for instance, one ultraviolet photon in the UVC range being absorbed on DNA can be dissipated into 30 or 40 photons in the infrared. And that is production of entropy. And that is apparently what is driving all of the irreversible processes, which no doubt life is one occurring in our universe, in fact. So we gave the example of dissipative structuring of adenine, and Claudette is working on the dissipative structuring of guanine. We think we have that more or less under control. I would like that she gives a talk on that, maybe next class, Claudette. You can answer me later if you like. But
yes,
if you can, if you have time to prepare for next class,
okay.
Give a short talk on guanine, how guanine is structured. And we also showed that many of the other fundamental molecules of life, that is the nucleic acids, amino acids, fatty acids, coenzymes, all absorb and dissipate within an interesting range of about, let's say, 210 nanometers to about 285 nanometers. And that turns out to be that photon range, just exactly where the photons have sufficient energy to break and then remake carbon covalent bonds, especially bonds which are double carbon covalent, which require higher energies. So the idea that organic molecules could be in space was first put forward by Fred Hoyle and Chandra Wickramasinghe. Now, Fred Hoyle was a nuclear physicist. He was, in fact, he is, well, probably those of you in physics know him, that he was rather famous for suggesting that the elements, the heavier elements, were produced in stars through nuclear reactions. And he wrote an article, in fact, in 1957 with a collaborator who gave him the data, but the idea was really Fred Hoyle's. And in 1983, they gave, and his collaborator's name was Fowler. And in 1983, they gave the Nobel Prize to Fowler, but not to Fred Hoyle. And well, there was a lot of talk about that. Why didn't they give that Nobel also to Fred Hoyle? And the reason appears to be that Fred was very critical of other scientists who have also won the Nobel Prize. And those who have won the Nobel Prize, of course, on the committees of giving out the Nobel Prizes. So it seems to have been a personal slight that one or a few of the members on the committee didn't want to include Fred Hoyle in the Nobel Prize, but really the author, the intellectual author of the paper was Fred Hoyle and not Fowler. So it's an interesting story of how politics gets into science. But anyway, Fred and Chandra were the first to postulate and the first to discover evidence of complex organic molecules in space. They first entertained the idea that those molecules were graphite grains, so carbon grains, like little sand particles made out of carbon. And they put that forward in 1962 in a paper. But later they developed that into what they were finding in space through the infrared emission lines and also the absorption spectra, absorption in the UV and visible, were in fact organic polymers. And that paper was published in 1974. And then through some surprising comparisons with the absorption spectra of bacteria, freeze-dried bacteria on Earth, comparing it with the absorption spectrum of light from stars behind the gas clouds in space, they came up with the idea that there are bacteria in space. Now they didn't say living bacteria, but the fit was it looked so perfect that to them there could be no other possible explanation for this, that there must be bacteria in space. And of course, they were heavily criticized by the biologists, who knew, for instance, that bacteria could not be thriving at those temperatures, and very doubtful that even the spores could stay alive for such a long period or propagate, not necessarily stay alive, but propagate for such a long period. And so it was rather a complicated time for the two. They are really let's say, the grandfathers of organic molecules in space. And most people have been denying their work, because their original work, before they got to the bacteria in space idea, has stood the test of time. And they were really the ones who were leading the field. They're very rarely cited. I think only now that history is looking back on all this and realizing that they are the two originators, which we should give credit to. So the density of the gas and dust clouds in space are very low. They are about 1,000 to maybe 10,000 particles per cubic centimeters. And the temperatures, well, are probably around 10 to 100 K. So they're not very conducive. This environment is not conducive to chemical synthesis. But we can, as I mentioned, employ ultraviolet light to do photochemical reactions and thereby produce some of these chemicals, these molecules, these chemical reactions occurring in outer space to produce these molecules. So just to mention this bacteria in space idea, you see the points here. This is the infrared emission spectrum coming from our galaxy, in the center of our galaxy. So if you look at the center of our galaxy, you will find a spectrum more or less of this form. Now, if they take freeze-dried bacteria, so those are the points, the data points are the astronomical points. If you take freeze-dried bacteria, you will also get, and then excited with ultraviolet light, you'll also get an emission spectrum, and that is the solid line. So there's rather a surprising fit of the astronomical data with the emission data of freeze-dried bacteria, particularly E. coli bacteria, which are the bacteria which colonize our intestine. So that it was this graph, in fact, which led them to the idea of bacteria being in space, and there was no other. They tried many other possible ideas, with silicon particles and carbon nanoparticles and all kinds of other attempts to fit the data, and this was by far the best they could do. So they came out with this paper suggesting that there was in fact bacteria in space in 1986. And so this is now just a description of what kind of emission one could expect in what wavelength region for the different molecule parts, the different stretching or bending or flexing. So these are in this range, correspond to the different possibilities in this range, and we see that there are a number of different rather complex vibrational motions which could give rise to different frequencies, and that gives rise to the spectrum. Now we also have absorption spectrum. Okay, so that is when we look at light coming from behind a gas cloud and knowing its spectrum of the star or estimating it, we can then plot a graph of the absorption as a function of wavelength, for instance, or in this case, it's the reciprocal of the wavelength, 1 over the wavelength. So the wave number. And this is for a region of inverse 1 to 3 microns. And again, the fit with the hollow spore forming bacteria fits very nicely with the observational data. The spore forming bacteria are the solid line, and the astronomical data of the absorption are these points. So not only the emission spectrum, but also the absorption spectrum fit very nicely with the bacteria. So this is the same now. This is the 1 to 3 inverse micron range. So that was in this range here, 1 to 3. And now these are data which are being a little bit more extended, a little bit later in time. And now what I want to point your attention to is this peak here. So this is, remember again, this is the absorption of the gas and dust in our galaxy. Okay, it's a function of 1 over the wavelength. So now what is interesting in this peak is that here we see it peaks at about 217.5 nanometers. And that corresponds to conjugation. Remember, I mentioned in an earlier talk that if you have conjugation that is double bond, single bond, double bond, that's double conjugation. Then the absorption is about 220 nanometers, or about 217 nanometers. So that is double conjugation. And if you have triple conjugation, we get absorption at 260. And that is, for example, benzene, which has triple conjugation, the nucleic acids, okay, the bases, adenine, guanine, cytosine, thymine, they all have Are you still with me, guys?
Yes, they're here.
Something happened. I'm gonna try going back. Okay, so did you hear? I'm not sure when we got cut off, but were you listening to this explanation about the double conjugation and triple conjugation here? Absorption at 220 and 260 nanometers.
We lost you here at this point.
Yes. Okay. So this peak then, which is the absorption peak, fits very nicely in what we have been saying in the class, in which we are dissipatively structuring carbon covalent bonded molecules in this region between about 286 nanometers and about 181. Now, if we go at lower or shorter wavelengths than 181 nanometers, then we start ionizing the molecules. So they start breaking apart. So they're not going to be absorbing anymore. So this is a very interesting finding that we're getting dissipative structuring of carbon molecules in interstellar space between about 181 nanometers and about 286 nanometers. Just like we're getting on Earth. Although on Earth, we're probably starting at about 220 because we had carbon dioxide and hydrogen sulfide absorbing shorter wavelengths, so they weren't arriving at the surface. But we could also have dissipative structuring all the way down to maybe 180 nanometers, at which point the ionization starts to break the molecules apart. So this is interesting data. And so this is the bacteria here. This is this bacteria with aromatics. And this is assuming that we have nanostructures like these spores, bacterial spores, which are also doing some reflecting. Okay, reflecting is also causing extinction. So that was the idea of Hoyle and Wick-Ramasinghe. Okay, but the interesting point I'd like to make is that we seem to have dissipative structuring of carbon-based organic molecules in interstellar space, giving rise to this peak in the absorption spectrum. It doesn't want to change. No? Okay. So remember again, this is the spectrum of the emission spectrum, infrared emission spectrum of E. coli bacteria. So this is in fact was the original by Hoyle and Wickramasinghe. This is the fit that they got. But now Pendleton and Ayamadadola in 2002 did the calculation again more carefully. And this is the fit that they get. This is what Hoyle and Wickramasinghe got, and now this is what these people here got. And this is the E. coli emission spectrum. So we're only in a much larger range. So we're only looking in this region here. Okay, this region here is blown up here. But now what they did was also fitted to dust, which was taken from a meteorite. This is the Murchison meteorite, which fell over Australia. And they collected it very quickly after it fell, I think in the 70s. And they analyzed the dust spectrum, the absorption, the infrared emission spectrum, and they got a much better fit using the dust of the meteorite than they did using the freeze-dried bacteria. So they suspected that it's not freeze-dried bacteria that are in space, but molecules which could be found in the Murchison meteorite. And so those molecules have been identified. Some of them have been identified in this meteorite. And well, there are a number of them, but the interesting thing is we have these amino acids and we have these purines, which are adenine, xanthine, guanine, and uracil. And the pyrimidines, uracil is pyrimidine. And a number of other organic molecules. So these guys here show that the fit for the emission spectrum is better using the organic molecules which are coming out of the meteorites. And we'll see that also in these meteorites, they contain maybe about 30 or 40% of what are known as polyaromatic hydrocarbons. So they're like benzene molecules, which are stuck together to forming these two-dimensional sheets, which we'll see in a future slide. And so here they are. These are the polyaromatic hydrocarbons. So they're basically benzenes, which have come together, but there are not only carbon, but also oxygen, nitrogen, and hydrogen. And they have a general size, which are greater than about 50 atoms. And so they are absorbing light in the UVC range and dissipating it into the infrared. Now, in outer space, there is no solvent. There's no liquid water that these molecules could dissipate into. You remember that with adenine and guanine in water, we excite the bases, and they, through vibrational dissipation, they go to the ground state, but by emitting the energy into the water. So in this case, in which there are no solvents in interstellar space, then how would the system dissipate itself? You know, you would excite it with absorbing an ultraviolet photon. It could be converted into vibrational motion, but the fact that there are very few other molecules or other dust or material in the environment, because remember the density is very low in space, and it's very difficult to dissipate this energy into the environment. Of course, it can do that to radiation. But if we want to increase the amount of dissipation, we want to shift the dissipation further towards the infrared. And how do we do that? Well, we can do that by increasing the size of the molecule. Because if we increase the size of the molecule, then we get more vibrational states at a lower frequency, at larger wavelengths. So it can emit farther into the infrared. So that is one reason, possible reason, why they are finding that these are rather large sheets, because they